This video is for Chapter 8, Section 6, and it's all about vectors. This is our first introduction to vectors, and it's going to be a lot of information. This video is very important because I'm going to be going through a lot of definitions and the basic ideas behind vectors, and then we're going to spend a lot of time in class actually working with them in regards to material that we've already seen. So, vectors, let's first go through what are they. A vector is a quantity with both magnitude and direction. So if I was to say something like, I would like to travel 20 miles, that's not a vector because I have no direction. Or I'm going to walk to the right. Well, that's got direction, go to the right, but no magnitude. You have to really describe how far you want to go and exactly what direction. That's a vector. So let's take a look. They're going to be represented by an arrow to show size, so we've got to show how long it goes, there's your magnitude, and direction. The arrow points where it's going. Now the hard part about a vector, like this vector for example, is 10 units long, and it tells you it goes from point A to point B. It's not a segment, but it does have a starting and an ending. It goes from A to B. But it's very specific that it goes from A to B and not from B to A. There is a very specific direction. So we might say, if we had these letters, we might call this vector AB, and we'll put a vector symbol. Now, the key is that I didn't finish the arrow. It's not a ray. It doesn't go beyond B. It stops at B. From A, go to B and stop. Here's another vector. This vector goes straight down. So it has a direction. It goes 5 units down. Now that vector could occur right here. There's another vector that goes 5 units down. They are the exact same vector because vectors only care about size and direction, not where they start. So a vector that goes 5 units down is the same as all vectors that go 5 units down. Now, there are going to be two ways that we describe vectors. One, we're going to describe them with their magnitude and direction. An example of that would be to say 10 units at 30 degrees south of east. So 10 units, that's our magnitude, that's our size. 30 degrees south of east, there's our direction. Here is a picture of it. Now, we might think of this as the origin on a graph, but it's not the origin of graph, it's just the origin of our vector. And our vector goes 10 units, so this point right here is 10 units away. And notice the 30-degree angle is always created from where the vector starts, and it created by opening to the south of east. So see, I am pointing south of the east mark. Not here. If I put the angle here, that would be opening to the east of the south marker. I want to open 30 degrees south, so 30 degrees down from east. So that's one example. That's what magnitude and direction looks like. It has a distance and an angle based on compasses, north, east, west, south. Okay. So, or now northeast, southwest. Our second idea are called coordinate vectors. Now, coordinate vectors show up a lot more in mathematics, in programming, in computer design, graphic design. Coordinate vectors, we're going to talk two-dimensional here, have an x and a y, just like coordinates on a graph. And the x tells you how much it moves from right to left, and the y tells you how much it moves up and down. So, right is positive, left is negative, up is positive, down is negative. So when I see negative 8, 6, this is a vector that is telling me to go left 8 and up 6. Now interestingly, if you're really paying attention, left 8 is its own vector. I could be standing right here and say go left 8, and then I have to go up 6. Each one of those is a vector. But we are looking at the combination. Here's left 8, here's up 6. Together they make the vector negative 8, 6. Together they make the vector. Now, be careful. You don't build 8 and 6 from the same spot. You have to go 8, then 6. You could do it backwards. You could say that it goes up 6 first, and then left 8. But it has to go one and then the other. The negative tells us left, the positive tells us up. The one thing about this 8-6 is it doesn't start from the origin. It could be anywhere. I could put a dot on any wall in this classroom and say vector -8-6, and you would go left 8, up 6. On your paper, on a desk, anywhere. It doesn't have to be from a specific place. All right, so that's my definition of vectors, their magnitude and direction, and their coordinate vectors. What I'm going to look at now is we're going to combine the two and look at the relationships. And those relationships are going to be the key to the examples that we do in just a second. So here is one picture with one vector. Here's our vector. And I have all the parts. Here's its magnitude. Here's its direction. Here's its x movement. Okay, right, left. Here's its y movement. So there are two different ways to describe this vector. M units at d degrees, and then north of east it looks like. Or I could describe it as x comma y. The key is to look for some relationships. Like how about this relationship? M squared, the hypotenuse, is equal to x squared plus y squared. There's a Pythagorean theorem in this, and that is very important. I can find m if I had x and y. I can also find d if I had x and y, because the tangent of d degrees is equal to the opposite over the adjacent, y over x, in this picture. It is not always y over x. It could be x over y. If you're writing notes down and you put this down and think that it's always y over x, you're not making the right notes. You need to put a star here and say it could be x over y. Then I have, well, what about the other relationships? What if you have d and you have m and you need to find y and x? So an interesting one that I see is that the sine of d degrees is equal to y over m. And if I was to multiply by m on both sides, I would get m times the sine of d is equal to y. Now the exact same relationship can be laid out for cosine. The cosine of d degrees is equal to x over m. Multiply by m on both sides, and you get m cosine of d equals x. Now these relationships are not always there, in that tangent could be x over y. And if it switches, if it's x over y, okay, depending on the picture, then these will also switch. Because if y and x switch in terms of where the angle is, then they will switch in terms of opposite and adjacent. So be careful that when I do my example in just a second, I'm going to show this. What's important right now is that we understand that magnitude, direction, x and y have a bunch of relationships. There's a Pythagorean theorem for m, there's a tangent for d, and that a combination of sine and cosine will find us x and y. Let's take a look at how this works and see if we can understand some of this material. All right, let's look at a few examples of how this might work out for converting from coordinate form to magnitude and direction form. We're going to start with my first example. Convert 10 units at 40 degrees west of south into a coordinate vector. First, look at my picture. Does it make sense? 10 units at 40 degrees toward the west. So I better put in pointing west of south. Now this is a really important example because it's going to show that switch that I was talking about. In this case, I have the hypotenuse and I have the angle. I don't want to put x and y over here because I need my right triangle to be around my angle. So x is my opposite, 10 is my hypotenuse. I have the sine of 10 degrees equals x over, or sorry, it's the sine of 40 degrees, whoops, x over 10. So I'm going to multiply by 10 on both sides, and so I've got 10 times the sine of 40, and I have an answer of 6.4. So approximately 6.4 is my x value. Now I go to do y, and y is the adjacent side. So cosine of 40 degrees is equal to y over 10. I'm going to keep using the 40 and the 10 because I know those are correct. And now I've got 10 times the cosine of 40. And that answer is approximately 7.7. So 7.7 is approximately my y. I am done. I have converted this into coordinate form, except I need to make sure direction is maintained. This is clearly going to the left, and it is clearly going down. So I need to put that into my numbers. Left is negative, so 6.4, and down is also negative, so I'll put negative 7.7. That's my first example. Notice that sine this time was x because things got shifted around. Now I have another problem here. This time that angle is in here, opposite it is actually the y, adjacent is the x. These things change. It says convert, now that I wrote this as a point, so I'm going to change this right now. The vector right 8 down 15 into magnitude and direction. Right 8 down 15. So our first relationship was to remember the Pythagorean theorem. 8 squared plus 15 squared equals the magnitude squared. So 64 plus 225 is equal to magnitude squared. 289 equals magnitude squared. Take our square root, and 17 equals our magnitude. We have now found m. Now to find our degrees, we're going to use the opposite and the adjacent. So we have the tangent of d degrees equals 15 over 8. This is where we use our inverse tangent of 15 over 8, and we're going to be done here. So I've got second tangent 15 divided by 8, and I find out that my angle is approximately 62 degrees. D equals 62 degrees. All I have to do now is write up my answer. This is 17 units at a 62 degree angle, but I need to describe that angle. Well, if I put a little arrow in, this angle is opening down, so it's opening to the south from the east. So south of east. 17 units at 62 degrees south of east. Example number 2. Example number 3 is a word problem. A boat travels 12 miles per hour east while the current of the river that it's in pushes it 5 miles per hour north. So how far does the boat travel in 1 hour? The motor is pushing it 12 miles per hour, but the river is pushing it 5 miles per hour. So we're going to have to draw our own diagram. East on our compass is going to be that way. So it's going to go 12 miles per hour east while it gets pushed 5 miles per hour north. Now, so you have to put one and then the other because it's kind of like a coordinate vector. You never start the vectors from the same spot. One, then the other. Combined, the boat should be pushed north and east. So this is our magnitude, and now here's our direction. All from the starting spot. This example now looks exactly like example number 2. I've got a Pythagorean theorem for my magnitude, in which 25 plus 144 equals 169. Square root that, and we have 13 equals my magnitude. So the boat is actually traveling 13 miles per hour, but I need a direction. Well, I have a tangent of d degrees equals opposite over adjacent. So I use my inverse tangent, and I have the inverse tangent of 5 over 12. And my direction ends up being second tangent, 5 divided by 12, 22.6, let's call it 23 degrees. Approximately 23 degrees. So I can finish by writing the same statement as this, where I'm going to say the boat is traveling 13 miles per hour at 23 degrees. And how would we describe this? Well, it is going north of the east axis, and it's headed north. North and east are the two directions that should show up. So north of east. In class, we'll do more examples to understand direction. The key here is to see that the Pythagorean theorem, sine, cosine, and tangent are the keys for switching back and forth between the two different types of vectors. Hopefully these examples will help get you started on this final assignment for this level. And that's it for Chapter 8, Section 6.